For decades, data engineering has relied on a foundational premise. Storage is a passive container, and data simply sits inside it, waiting for a processor to arrive and act upon it. That premise shaped the data file formats we still use today. Formats like Apache Parquet and Orc were engineered around the hardware realities of the early 2010s, where network bandwidth was limited to 10 gigabits per second and spinning magnetic disks were the primary storage medium. The data pipeline chokes when the structural layout of the file cannot keep pace with the physical throughput of the storage hardware. This visual represents the kinetic energy of modern data hitting the wall of legacy software. Today's enterprise environments run on 100-gigabit networks and multi-terabyte NVMe storage arrays. These systems deliver data so fast that a modern CPU core cannot decompress the incoming files quickly enough to maintain full throughput. The bottleneck has inverted. Raw storage capacity and network speed are no longer the limiting factors. The physical architecture of the passive file itself is now the primary constraint on hardware performance. Within the Datatism T7 framework, the T6 technology dimension provides the lens for understanding this system evolution. It maps how infrastructure reacts when its logical constraints are overtaken by its physical capabilities. Traditionally, a rigid vertical line has separated these two components, the active query engine, which performs the work, and the passive file format, which holds the record. Under the execution pressures of modern analytical workloads, this precise boundary is collapsing. This shift introduces a concept we will explore through the latest research in the field, the move towards autonomous computational structures. The evidence suggests that to eliminate modern hardware bottlenecks, the file format must begin to function as an active participant in the data pipeline. Apache Parquet was engineered to prioritize disk density. It achieves this by layering heavy block-level codecs, like ZSTAD and Snappy, on top of internal columnar encodings. Reading a single value requires decompressing an entire 1 megabyte page into memory. Standard decoders max out around 3 gigabytes per second. While the CPU core is saturated unpacking data, underlying NVMe arrays sit idle. While heavy compression saves on storage costs, it has become a significant performance constraint for high-speed analytical engines. Machine learning workloads have shifted toward ultra-wide feature tables. These datasets often contain tens of thousands of sparse columns used for training. Parquet relies on the Apache Thrift protocol for its footer metadata. On tables of this magnitude, parsing those footers causes massive CPU spikes before a single row is read. Meta-Nimble addresses this by replacing the Thrift protocol with a custom flat buffers architecture. Flat buffers enables zero-copy, constant-time offset lookups. This allows the system to locate data points without a separate CPU deserialization phase. For hyperscaled machine learning pipelines, reducing metadata parsing time from seconds to milliseconds is an architectural requirement. Beyond metadata, the physical arrangement of bits on the storage medium must be reconsidered to take advantage of modern processor instructions. The CWI Fastlanes project departs from traditional monolithic codecs by focusing on low-level bit layout. Traditional formats store integers sequentially. This forces the CPU to process values one at a time, creating a queue that wastes chip bandwidth. Fastlanes utilizes a transposed interleaved layout. The bits are transposed and stacked so that values are spread across registers in a repeating pattern. This layout is designed to align with 1024-bit virtual SIMD registers. This arrangement allows standard, portable scalar code to be automatically vectorized by compilers, ensuring the same logic runs at peak efficiency across architectures. Benchmarks show this hardware alignment enables decoding speeds of over 100 billion integers per second, or 40 values per cycle. To saturate modern silicon, data must be prearranged specifically for parallel consumption. The LAI Vortex framework introduces a design that decouples the logical array from its encoding and its physical layout. Conventionally, a query engine must decompress a chunk of data into an uncompressed memory buffer before it can apply a filter. Vortex utilizes compute kernels that operate directly on the compressed representation. It evaluates filters against dictionary keys or bit-packed integers without expanding them. This entirely removes the need to materialize intermediate uncompressed buffers, saving memory and CPU cycles. When the execution logic can run directly on the encoded data, compression shifts from being a storage penalty to an execution accelerator. This rapid advancement in custom encodings introduces a significant risk to long-term data accessibility. If every system uses a unique layout, future query engines may lose the ability to interpret the data stored today. The CMU Tsinghua F3 format addresses this by embedding compact WebAssembly bytecode directly within the file's metadata. A query engine reading an F3 file can pull this embedded decoder and execute it within a secure sandbox. By decoupling the decoder from the query engine, F3 provides a pathway for data to remain accessible, turning files into independent, self-executing binaries. Despite these technical shifts, Apache Parquet will remain the enterprise standard for cold archival storage and broad vendor interoperability. The system architecture is shifting toward a format-aware translation layer. Engines like DuckDB interface with multiple physical formats simultaneously, rather than forcing a single storage standard. This allows the engine to dynamically map specific query workloads to the physical representation that best suits the task. This abstraction protects long-term pipelines from premature standardization while allowing for extreme hardware optimization on active, performance-critical workloads. Interoperability is now an ecosystem property, not a benchmark metric. The post-Parquet landscape is defined by the coexistence of these specialized formats. This trajectory brings us back to the Datatism T6 technology dimension and the changing nature of the data file itself. We have seen the evolution from passive containers designed for capacity to hardware-aligned layouts to storage that encapsulates its own execution logic. This profound transformation represents the total fusion of compute and storage elements at the base of the technology stack. The shift is clear. Data is no longer a static artifact that we process. The data now carries the internal logic required to participate in its own execution. Designing for this hardware reality means moving past the concept of a passive container and treating the file format as an active component of the computational architecture.